In this lesson, the goal is not to solve a long numerical problem yet. The goal is to meet the operational amplifier, or op-amp, and understand what kind of circuit element it represents. An op-amp is built from many transistors, resistors, capacitors, and diodes, but in circuit theory, we usually treat it as one block. That block can be used for comparison, voltage following, inverting amplification, non-inverting amplification, summing, differentiation, integration, and many other operations. So the name operational amplifier is literal. It is an amplifier used to perform operations on signals. Now let us connect the physical part to the schematic symbol. A common op-amp, such as the 741, has several package pins. For circuit analysis, the most important pins are the inverting input, the non-inverting input, the output, and the two supply pins. The inverting input is marked with a minus sign. The non-inverting input is marked with a plus sign. The output is drawn at the tip of the triangle. The supply pins, V plus and V minus, power the device, even when they are not always drawn in every small signal schematic. For the first pass, we use the ideal op-amp model. There are three assumptions to keep in mind. First, the open loop gain is extremely large, so ideally A goes to infinity. Second, the input resistance is extremely large, so no current enters either input terminal. We write I plus equals 0 and I minus equals 0. Third, the output resistance is approximately 0, so the op-amp behaves like a strong voltage source at its output. The basic controlled source idea is V output equals A times V plus minus V minus. The ideal model is a tool, not a real power supply. In a practical op-amp, the output voltage cannot become larger than the supply rails. If the op-amp is powered from plus VCC and minus VCC, then the output is limited to that range. When the requested output tries to go beyond the rail, the waveform clips. So when we analyze op-amp circuits, we first use the ideal rules, but we also remember that the final output must stay inside the available supply range. The plus and minus signs tell us the direction of the effect. If the non-inverting input, V plus, becomes larger, the output tends to rise. If the inverting input, V minus, becomes larger, the output tends to fall. That is why the upper input is called inverting. A positive change there pushes the output in the opposite direction. This sign convention is the key to understanding why feedback can force the two input voltages to become almost equal in many linear op-amp circuits. Here is the first circuit we will recognize, the basic inverting op-amp. Read it slowly from left to right. The input voltage Vi passes through resistor R1 and reaches the minus input node. The plus input is connected to ground. The output is VO on the right. A feedback resistor RF connects the output back to the same minus input node. This feedback path is not decoration. It is the path that makes the circuit operate as a controlled amplifier instead of as an open-loop comparator. Let us mark the important parts. The red path is the input path through R1 into the minus input node. The orange path is the feedback path through RF from the output back to that same node. Because the ideal op-amp input current is 0, almost no current enters the minus terminal. Since the plus terminal is grounded, V plus is 0. In the next lesson, negative feedback will let us treat the minus node as almost 0 volts as well. That idea is called virtual ground, and it leads to the inverting amplifier gain formula. So the handoff from this introduction is simple. An op-amp has a plus input, a minus input, an output, and supply limits. In the ideal model, the input currents are 0. The input resistance is infinite, the output resistance is 0, and the gain is very large. The first circuit to recognize is the inverting op-amp. Vi goes through R1 to the minus input, the plus input is grounded, and Rf feeds the output back to the minus input. Next, we will calculate exactly how that circuit amplifies and inverts the input signal.